So welcome to this video, which will be useful for both lectures, lecture 5 and lecture 6. Lecture 5 is on logical signals and Boolean algebra. Lecture 6 is on logic function representations, and both lectures are part of the combinatorial logic series of lectures. So what you're going to see here is an example of putting Boolean algebra in practice. And we're going to show this with a hypothetical alarm system logic circuit. But let's remind ourselves what we were taught during lecture 5, and more specifically, let's remember De Morgan's theorem. Now, according to De Morgan's theorem, as you should remember by now, if you're given a function with a series of variables and some or and ands over here, if you invert the function, then the result is the function, again the same function, only with all the operands being inverted, and all the operators themselves also being inverted. So wherever you got an xi variable, you will use a negated or an inverted, if you prefer to call it this way, xi variable. And wherever you had a plus symbol for an OR operation, you will have now an AND operation or a dot, and the other way around. And just to wrap up, we've said that De Morgan is very important because it allows you to simplify in Boolean expressions, which translates to more efficient logic circuits in terms of consumption, number of gates, and speed, power consumption. Now let's see that in practice with a hypothetical circuit. Suppose that you are asked to build the following alarm logic circuit, okay, with some SSI integrated circuits. As you can see already in the slide, we have 3 different inputs. A logical input for an intruder that is being detected, another logical input that is mapped to a smoke detection, and then you have a testing mode in case you're testing your alarm system. Obviously, you want the alarm to start making a sound when you got at least either of these two being true. So the only thing that you need is an intruder to be detected or smoke to be detected. Or if you are that unlucky and you have installed in your house such an alarm system, there is both smoke and some intruder. So as you can see here, it's very easy to understand we've got an OR gate. We also have a testing mode, which goes through a negation. And the reason we do that is that we feed both the result of the OR gate and the NOT gate to an AND. If we want to test the alarm system, we push a button, then whatever is true over here is converted into false and essentially deactivates the alarm, because the AND will never be wanting the output if you're on a testing mode. Okay, so let's see this in practice. Imagine that it would look like this. And let's just pay attention to the colors over here, because it's going to be useful for the next slides. Got an OR gate, got a NOT gate, and a final AND gate for the alarm. And this is how you would do it with some SSIs. Again, the colors are mapped to the logic circuit over here when you're using SSIs to implement it. And finally, the final output from the last AND gate triggers the alarm. Okay, let's see how you would simplify this. Suppose that you have no AND gates, okay? You got De Morgan's rules or theorem, if you want, to help you here. So as you remember by De Morgan, if you invert an AND operation, then this is equal to inverting each variable and replacing the AND operation with an OR operation. Now think about the AND gate you got here. Again, by applying De Morgan's rules. If you negate an AND, essentially you got an OR gate with negated input. Now think about the AND gate with the NOT gate here. If you apply another NOT gate, which you cannot see here on this part, it would essentially give you back an AND gate, wouldn't it? So by applying a NOT after the OR over here, you can say that the equivalent of an AND gate is an OR gate whose inputs are negated and also the output is also inverted. So all that from De Morgan's rule. So how can you take advantage of it? Well, if you replace the previous gates in the alarm system, it will start looking like this. If you replace the last AND gate with an OR gate whose inputs are inverted and the output is also inverted, it will look like this. Okay, at this stage it might look a little bit more complicated. However, notice that you have two NOT gates in series. You can actually get rid of them. So now it looks far more simple, doesn't it? You have two OR gates and some NOT gates over here, and this is how you would implement it. And as you probably remember from our previous lecture, a NOR gate plus a NOT gate at the end, you can replace it with a NOR gate. Now let's see how you can make it possible to represent any Boolean function only with NOR gates. Again, we've got our alarm system over here as an example, and you've seen that we have converted it to two NOR gates over here. Let's interpret that. So the alarm equals an intruder or smoke detection times testing, negated, of course. Let's rewrite that to make it look simpler. A equals I plus S in a parenthesis times the inverted testing mode. By applying De Morgan, you can rewrite it like that. If you invert A, then you're essentially inverting also the right side over here. But as you know from De Morgan, this would mean that you replace the logical AND here with a logical OR, and you invert both sides here. So if you invert the testing mode, it will be T over here, and you invert also whatever is inside the parenthesis. Also, you replace the OR operation with an AND operation. Now again, we can apply De Morgan on the parenthesis here. If you apply De Morgan over here, the result of the whole parenthesis is inverted, and so are the variables inside, and so is the operation. So far we have that the inverted A equals the inverted OR of I and I or S, or the testing mode. Now if you apply theorem 4 and you invert both sides again, you end up in this. The alarm system is equal to a big parenthesis inverted of an OR operation between the testing mode, and the inverted or between an intruder and a smoke detection. Now let's see how you would implement the alarm system, only this time using only NAND gates. So we start with our logic expression over here. That is an equivalent of the alarm configuration with gates over here. And we apply T4. Now remember that T4 stands for the involution theorem, according to which then the inversion of your inverted self is again yourself. So inverted A, inverted again, is equal to A, and so does whatever is on the right side. In red you can see the extra parentheses and the inversions. And then we apply De Morgan. We're going to apply De Morgan on the inside parentheses, as a result of which the inverted T will be replaced by T, and also we need to invert whatever is on the other parenthesis over here and replace the AND operation with an OR operation. We apply again De Morgan, this time on the parenthesis over here, and we get this result. So far we've managed to have two inverted versions of variables in an AND operation, but we're still not there because we have an OR operation here. Remember, we want NAND gates only. So we apply De Morgan again. Notice that we don't have an inversion on the external parenthesis here because we applied De Morgan. We are close, but we are not there yet. We apply the same theorem again, theorem T4, in other words, the involution, and we are finally there. If you check out this series of logic operations, they translate to a series of NAND gates. Specifically, you got the NOT of this AND over here, and you got the NOT of this AND inside the parenthesis here. Okay, now let's see how you would go from here to a NAND implementation. We got the NAND gates here, and we got our inputs. The intrusion detection, smoke detection, and the testing mode. Remember that we only have NAND gates, which is why we use the NAND gate here by passing the same variable twice in both inputs. So every variable which is passed twice from a NAND gate, it works like a NOT gate and it inverts the input. So far we got everything that we need. We've got the inverted I, the inverted S, and the inverted T by using this trick over here. The next thing to do is to pass the results in another NAND gate, which is mapped to this parenthesis over here. Now, the result of here, along with the result of T inverted, is passed to another NAND gate. And because of the most external parenthesis, which is again an inversion, we use a last gate over here, a NAND gate. Again, we use the same trick. We pass the last output as twice the input, and you get the final result. So this is how you would implement the same circuit with only NAND gates by using a series of De Morgan applications plus the T4 rule. So suppose you're given again the same circuit that only has NAND gates. This time we're going to follow a different approach and again result in a NAND only implementation. To do so, we start with our expression as we know it, and this time we try distributivity. According to distributivity, whatever you got on this side will become I times T inverted, or S times T inverted. And then we apply rule T4, which is the involution. So we invert and then we invert again. And the reason we do that is because this allows us to apply De Morgan. Now, as you can see here, we have applied De Morgan first over here. Side, you see in the parenthesis over here, we got the terms I and T inverted. And we've also applied it to S and T inverted. And of course, we changed from an OR operation to an AND operation. So overall, we have a series of AND operations and a lot of inversions over here. So with far less steps, by using more theorems, not just De Morgan, we ended up in this implementation that has only NAND gates implied. Now, in order to end up in this, my advice to you is to start from the external parenthesis. So this is the whole result A, and it is inverted, so you put a NAND gate over here. Now, what are the inputs of the red NAND gate? Well, whatever you got in the green parenthesis. So this is the first one, and this is the other one. Now, if you try to interpret these with NAND gates, obviously what you get is an S input from this side and an inverted T input from this side. Again, you see that you need an inverted T input over here, so you can bind them together. And you need the I input. The only thing which is missing is how to invert T, and as I told you earlier, you can do that by passing T twice to the NAND gate. So with far fewer steps, we ended up in an implementation that uses only NAND gates. So we've reached to the end of our example. There are some take-home messages here. We've seen that you can use theorems in order to manipulate Boolean expressions, and you do that in order to simplify them and to meet with some design challenges, such as if you're given a very, very simple specific type of a circuit, then by manipulating Boolean expressions, you can actually end up in a design that implements the system that you want. But as you've seen, all manipulations we've used so far were based on intuition, which is why this video is an example that bridges whatever we've explained during our 5th lecture on logic signals and Boolean algebra, and the next lecture on logic function representations. In the consequent lectures, we're going to try to address this question here, which is there a more systematic way to obtain the minimum version of a Boolean expression? So far we've been doing things with intuition, and we are going to do in the future minimized versions of what we want based on a more systematic approach.